Hello and welcome back to Introductory Astronomy. In the late 1970s, cosmologists trying to piece together the evolution of the universe were confronted with two nagging problems that had no easy explanation within the standard Big Bang model. The resolution of these problems has caused cosmologists to completely rethink their views of the very early universe. The isotropy of the microwave background indicates that regions A and B in the universe were very similar to each other when the radiation we observe left them, but there has not been enough time since the Big Bang for them ever to have interacted physically with one another. Why then should they look the same? This is what we call the horizon problem. When observed in diametrically opposite directions from the Earth, cosmic background radiation appears the same, even though there hasn't been enough time since the Big Bang for them to be in thermal contact. We also have what is called the flatness problem. In order for the universe to have survived this long, its density in the early stages must have differed from the critical density by no more than 1 part in 10 to the 15. Why? Because if the universe does deviate even slightly from critical density, that deviation grows rapidly in time. For the universe to be as close to critical as it is today, it must have differed from the critical density in the past by only a very tiny amount. Between the God epoch and the quark epoch, some parts of the universe may have found themselves stuck in the unified condition longer than they should have been. This resulted in an extreme period of inflation, as shown on the graph. Between 10 to the minus 35 seconds and 10 to the minus 32 seconds, this part of the universe expanded by a factor of 10 to the 50th. Thus, during the period of inflation at the end of the God epoch, the universe expanded enormously in a very short amount of time. Afterwards, it resumed its earlier quote-unquote normal expansion rate, except that the size of the cosmos had become about 10 to the 50th times bigger than it was before the inflation. The theory of inflation, if correct, would solve both the horizon and the flatness problems. This diagram illustrates how the horizon problem is solved. The points diametrically opposite from the Earth were in fact in contact at one time. So inflation solves the horizon problem by taking a small region of the very early universe, whose parts had already had time to interact with one another and that had thus already become homogeneous, and expanding it to an enormous size. In frame A, points A and B are well within the shaded homogeneous region of the universe, centered on the eventual site of the Milky Way galaxy. In frame B, after inflation, A and B are far outside the horizon, indicated by the dashed line, so they're no longer visible from our location. Subsequently, the horizon expands faster than the universe as a whole does, so that today, in frame C, A and B are just re-entering our field of view. They have similar properties now because they had similar properties before the inflationary epoch. The flatness problem is solved as well. After the inflation, the need to be exceedingly close to the critical density is much more easily met. Inflation solves the flatness problem by taking a curved surface, here represented by the surface of the expanding balloon, and expanding it to an enormously large size. To an ant on the surface, the balloon looks virtually flat when the expansion is complete. Cosmologists also realized that galaxies could not have formed just from instabilities in normal matter. Before decoupling, background radiation kept clumps from forming. Variations in the density of matter before decoupling would have led to variations in the cosmic microwave background. Galaxies or quasars must have begun forming by a redshift of 6 and possibly as long ago as a redshift of 10 to 20. Because of the overall expansion of the universe, any clumps formed by normal matter could only have had 50 to 100 times the density of their surroundings. Dark matter, being unaffected by radiation, would have started clumping long before decoupling. Galaxies could then form around the dark matter clumps, resulting in the universe we see today. So the formation of structure in the cosmos depended crucially on the existence of dark matter. In frame A, the universe started out as a mixture of mostly dark and normal matter. In frame B, a few thousand years after the Big Bang, the dark matter began to clump. In frame C, we see that eventually the dark matter formed large structures, represented here by the two high-density peaks, into which normal matter flowed, ultimately to form the galaxies we see today. The three frames at the right represent the densities of dark matter, in red, and normal matter in yellow, in the respective graphs at the left. And here we see a simulated structure of the universe. We have three views of a present-day 100 by 100 by 100 megaparsec cube in a simulated cold dark matter universe with critical density equal to 1. The cube expands with the universe so that it encloses the same material at all times. The three frames show the growth of structure resulting from the growth of small density fluctuations in the very early universe, displayed at redshifts of 6, which is 1 billion years after the Big Bang, redshift of 2, which is 4 billion years, and redshift of 0, which is present day, or 14 billion years after the Big Bang. Although dark matter does not interact directly with radiation, it will interact with the gravitational force, leading to tiny ripples in the cosmic background radiation. These ripples have now been observed. Here we have a Kobe map of temperature fluctuations in the cosmic microwave background over the entire sky. Hotter than average regions are in yellow, cooler than average regions in blue. The total temperature range shown is 200 millionths of a Kelvin. The temperature variation due to Earth's motion has been subtracted, as has the radio emission from the Milky Way galaxy, and temperature deviations from the average are displayed. And here we have a much higher precision map of the cosmic microwave background radiation. We have the entire microwave sky as seen by the WMAP spacecraft at frequencies between 22 and 90 gigahertz, which are wavelengths ranging from 14 to 3 millimeters. This new map may be compared directly with the Kobe map shown in the previous slide. The effective resolution of this WMAP, it's a multi-wavelength survey, is about 25 arcseconds compared with 7 degrees for Kobe. The inset at the right shows a 7 arcsecond resolution map of a roughly 2-degree patch of sky, obtained by the ground-based Cosmic Background Imager instrument at 30 gigahertz or 1 centimeter wavelength. The bright blobs are slightly denser than average regions of the universe at an age of roughly 400,000 years. They will eventually collapse to form clusters of galaxies. Here's a short summary of Chapter 27. At present, the universe is matter-dominated. At its creation, it was radiation-dominated. Matter was created by pair production. We do not understand the physics of the universe before 10 to the minus 43 seconds after it was created. Before that, we believe all four forces were unified. Gravity froze out first, then the strong force, then the weak and electromagnetic forces. Most helium and nearly all deuterium in the universe was created during the primordial nucleosynthesis. When the temperature became low enough for atoms to form, radiation and matter decoupled. The cosmic background radiation we see dates from that time. The horizon and flatness problems can be solved by inflation. The density of the universe now appears to be the critical density. 2/3 of the density comes from dark energy, and dark matter makes up most of the rest. Structure of the universe today could not have come from fluctuations in just ordinary matter. Fluctuations in dark matter can account for what we see now. Study Chapter 27.4 through 27.6 and be able to summarize the horizon and flatness problems and describe how the theory of cosmic inflation solves them. Understand the microwave background radiation and its consequences.